Today we'll tie the concept of universal gravitation to circular motion by looking at orbital motion in satellites. A satellite is a smaller body that revolves around a larger body, for example the Moon or the International Space Station. You may be wondering, if gravity acts down on the Moon, why doesn't it crash into the Earth? The Moon or any other satellite doesn't crash into Earth because of its tangential speed. Its tangential speed is sufficient to maintain orbital motion. Instead of falling into the Earth, a satellite falls around the Earth. Alright, so here we have the simulation of a satellite up here in the purple, that's going to orbit around this yellow sun or larger object. So let's say I can set the velocity down here, and we give this satellite an initial velocity of 0, and we can see what happens. Falls straight down, right? Blows up into the Earth. If I give it a tangential velocity here to the side, and let's say I made it 60 units, right? You saw the planet shot off to the side a little bit, but it was still ended up crashing down into the Earth, right? So not enough speed to orbit. If I give it too much speed, it flies out, never coming back. That's our escape velocity. At just the right speed, our satellite will achieve a circular orbit, right? Where it's falling around the Earth. Every time it falls, quote unquote falls, the Earth curves away from it. So it's in this stable condition of falling around the Earth. There are other types of orbits called elliptical orbits, where are kind of in between. So if it has a speed in between that just right speed and that escape speed, it'll have a elliptical orbit. So to summarize, if the speed is too slow, the satellite will crash into the Earth. If the tangential speed is too great, it'll escape from Earth's influence, and if it's just right, the satellite will maintain a circular orbit. How do we find the speed that is quote unquote just right for a circular orbit? To find the speed, we rearrange the equation for centripetal force using universal gravitation as our net force and solve for v. Though we're not going to show the derivation here, we get speed equals the square root of g times the mass of the planet divided by the orbital radius. Let's say we have two satellites that revolve around the Earth with the same orbital radius, but satellite A has twice the mass of satellite B. How do you think their speeds will compare? Well, it turns out they have the same speed because orbital speed is independent of the satellite's mass. Notice that our equation uses the mass of the planet, not of the satellite. Let's work through a couple example problems. The velocity of an object orbiting at a distance of 4.5 times 10 to the 7th meters from the center of a spherical object whose mass is 3 times 10 to the 23rd. All right, well, that's poorly written. They're asking us to find the velocity. So our orbital velocity would be the square root of g times the mass of the spherical object divided by its radius. So we're going to have the square root of 6.67 times 10 to the negative 11th times 3 times 10 to the 23rd divided by 4.5 times 10 to the 7th, and we're taking the square root of all that. So we'll multiply the top first. Right, and that gives us 2.0 times 10 to the 13th. So we have 2.0 times 10 to the 13th divided by 4.5 times 10 to the 7th. Divided by 4.5 10 to the 7th, which gives us 4.4 times 10 to the 5th. Now we got to take the square root, which gives us 667 meters per second, which we can round up to 670 meters per second. our next example, we're finding the velocity of an object orbiting at a height of 2 times the Earth's radius above the surface of the Earth. So the first thing we need to do is figure out what our radius is. So we have the radius of the Earth plus 2 times more above the surface. So our radius is going to be 3 times the radius of the Earth. We're using the same equation as before, square root of g times the mass of the Earth divided by this radius that we just found. So we have 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th, and then we're going to divide that by 3 times 6.4 times 10 to the 6th. So 6.67 times 10 to the negative 11th times 5.98, 10 to the 24th, gives us 3.99 times 10 to the 14th. On the bottom, we'll multiply 3 times the radius of the Earth, 6.4 times 10 to the 6th, which gives us 1.9 times 10 to the 7th. So we have 3.99 times 10 to the 14th divided by 1.92 times 10 to the 7th. 3.99 times 10 to the 14th divided by 1.92 times 10 to the 7th gives us 2.1 times 10 to the 7th, and then we're going to take the square root of that number, which gives us 4,558. So if we divide it, we get 2.1 times 10 to the 7th, take the square root, and we're going to round that up to 4,600 meters per second. Just want to point out real quick that for any of these practice problems that deal with the Earth and the 2 times the radius, this 3.99 times 10 to the 14th is going to be the same because we're multiplying the 6.67 times 10 to the negative 11th times the 5.98 times 10 to the 24th. So for the Earth, those two multiplied together will always give us 3.99 times 10 to the 14th.